Hi everyone, welcome to another episode of Challenging the Meaning of Intelligence, a series of video podcasts exploring how different forms of intelligence are transforming our present reality. The following is a conversation with Alessandro Confetti, Data and AI Solution Lead at Thoughtworks. In this episode, we explored historical and evolutionary perspective on intelligence, from Turing's Imitation Game to ELIZA and the metaphor of LLMs as stochastic parrots. We discussed notions of language and its impact on natural language processing. We deep dive on concepts of trust between humans and machines, and we also talked about the merging roles of large language models. Thank you, Thoughtworks, for hosting this insightful conversation. And as you know, this initiative is part of the research archive of LabCoexist. And now, dear community, here he is, Alessandro Confetti. Everyone, we're here today at Thoughtworks that is hosting the second chapter of LabCoexist podcast called Challenging the Meaning of Intelligence. And we're here today together with Alessandro Confetti. There is a very good friend that we met a long time ago in Politecnico, and then we have these talks every month to try to understand where this technology is taking us. And I was very flattering to have you and to have one of those conversations that we have every month happening
Thank
right
you very
now
much
and
for
to
the
share
invitation.
it. Exactly. So I leave to you a little bit of an introduction from you.
Very quickly, I'm happy to be here with you because also Ciro, we met long time ago. So it's funny how things and life somehow have intersecting patterns and paths ahead. And I'm working for Thoughtworks. I'm a data strategist, and I'm working on European customers that need to develop and arrive to a sort of conclusion with their data projects and AI strategies and implementations. And I'm very happy to host this second episode of LabCoexist, and let's start.
Thank you. Why we're here, okay, and I think this is very important. When we created this podcast, the intention was to understand, okay, how can we challenge this meaning of intelligence and the diverse forms that is undertaking right now in the different contexts and with the different influences that we're seeing. And I think I must accept that what we have seen and what we are acknowledging is that we're living a very interesting but complex moment right now, and with a lot of noise, okay? And I think one of the curiosities that I would like to hear from you, actually, and your point of view, is what kind of evolution have you foresee or have you perceived, okay, from decades or even before in historical times on the evolution in technology, and how can you compare it or what is happening right now? So what are the same things and what are the differences of what happens right now?
So looking back at history of the concept of artificial intelligence is actually very useful, because one of the main issues that we are facing today is that when we talk about artificial intelligence, we are talking about a very wide array of things.
Yeah.
And there is a lot of noise driven by marketing, by market, by investment. So it's important to somehow reduce this noise and these different meanings to something more manageable, more practical. And when you asked me to think about those things, I went back to a series of white papers or books that somehow helped defining this kind of concept over time. Of course, the idea of building something artificial that can be biological or mechanical or electromechanical is something that we played around with since very long time ago. We have ideas of this kind in the Greek mythology. We have a lot of books and science fiction books on the 19th century. Think about Frankenstein. Think about the actual book about robots.
Yeah.
That was were actually biological robots, not mechanical ones. But nowadays we are talking about artificial in a very specific context. I think this is very important from a starting point. So we're talking about something that is connected to digital computing. And this brings us back to somehow the origin of those things. So, and there is an interesting essay from Alan Turing that was published on the 1950, which is called Computer Machinery and Intelligence. And despite of the title, actually in one of the first paragraphs of this book, of this essay, that was published on a philosophical magazine of the time, but please, we need to remind that Alan Turing was a mathematician and a logician that was one of the, in my opinion, one of the three main characters of the revolution and also of the evolution of digital computing, alongside with Gödel on one side and Shannon on the other side. So it was a very capable mathematician, founded and defined what we call now today the Turing machine, so a universal way of computing with natural numbers, let's say this way, in basic set of instructions. So he wrote this essay to explore this problem about, can machine think? And the point was that he rejected from the very beginning of the essay the fact that we can define intelligence. He said it's a sort of lost cause. Many people think about intelligence in a different way. Let's try to refine the problem and say, can a digital computer think?
Yeah.
And to better specify how we can model this problem, he created a sort of fictional game, which is called the Imitation Game. That, by the way, is also the name of the famous movie that talks about another chapter of his life. And the Imitation Game, even if was defined 75 years ago at the end, is actually very actual, because it's the same pattern that we use today to demonstrate, to measure the capabilities of LLMs, artificial intelligence, and so forth. So let's play with Alan Turing. So Alan Turing says, okay, let's imagine a game in which we have a man and a woman behind a curtain, and they're also separated from each other. And on the other side of the curtain, we have an interviewer. Doesn't matter if it's a male or a woman. And the goal of the interviewer is to spot who is the woman. So the woman is playing, trying to demonstrate that she's the real one. And the man is actually playing to fake the interviewer in a sort of adversarial way. And the goal of the interviewer is to tell who is the man, so who is the woman actually, by asking things written on a typewriter, because we need to remove as much as possible small hints about the personality, the gender, and so forth. So going back to a very, very basic form of communication. And of course, you can ask whatever you want, and on the other side, they can play the game. Okay. And Turing says, let's imagine it is which, and we pull one, or the male or the woman, doesn't matter, and we replace it with one computer. So we have a man and computer, a woman and computer, and the game is the same. So again, the interviewer has to tell who is the human or the male, if you want to be more specific. Now, first of all, the interesting thing is that we're playing the same imitation game now also today, switching the interviewer. So whenever you go to a website and you are asked to demonstrate that you're a human playing CAPTCHA, you're actually playing an imitation game where the interviewer is a computer, by the way. And the interesting thing is that mainly we focus, so there has been a lot of debate about what does it mean, this kind of game. And the focus was on the people behind and the machine behind the curtain. But let's talk about the interviewer, because I think the framing the interviewer allows us to better understand the game we are playing even now today. So first of all, the interviewer sets the threshold of intelligence. If the interviewer is intelligent, it's able to frame if on the other side there is someone intelligent as him. But is also trying to falsificate, to demonstrate that one of the two is lying as an intention. And the way the game unfolds is also interesting, because, for example, one scenario that Turing was talking about was, say, let's imagine that you ask to do a very large computation. We know for sure that the computer is able to compute it very fast and in an accurate way. But should the computer answer immediately or not? Because if it answers immediately, you can spot it's a computer. So maybe it should fake and wait, or it should provide you a wrong result first. So again, this kind of game playing is what makes the imitation game very actual and problematic at the same time. But the key point is that Turing is not talking about intelligence, understanding. It's talking about thinking and speaking in a written form, which is a very interesting starting point. The second,
and lying, right?
Sorry?
Lying.
An intention in the communication. So what's your intention? Are you trying to demonstrate to be a human? So for example, is the computer aware of the fact that it's a computer, not a human? Or is programmed to think to be a human? Is lying or not? And what is the accuracy? And the other point is that there is a formal way to tell if you're a human or a computer, or it's based on trial and error and to a certain degree of certainty or confidence. Just to connect to what we are saying today, whenever you see, for example, the latest benchmark on DeepSeek, okay, you see the benchmark, you see the numbers, and you see some labels behind the numbers. That are the tests that were actually where the LLM has been tested against. Those tests are actually similar to the imitation game. So you are testing if it's capable of giving back an answer like a human. Yeah. You're not testing if it understands or other things. You're testing how much was the accuracy of the answers, how many answers were actually given. But there is another important aspect that is we need to frame. And Alan was framing it very correctly. So he says digital computer. So nowadays we have this kind of belief that everything is digital, but actually we have, at least historically speaking, two paradigms. The first one was the analog computing. So we have digital and analog computing. From a historical perspective, I rather say that we had before analog computing. So all the instruments to compute, for example, the astronomical computations about the movement of the moon and so forth, were analog computers. And analog computers have a very important feature. They are very fast, they are very efficient, but they have a limitation. They are programmed or built for a specific purpose. With Babbage and the analytical machine, we had the different paths. So the idea was, how can we build something that is mechanical in case of Babbage analytical machine, but that is able to compute natural numbers in a very effective way. Of course, we had a series of technical revolutions and also theoretical revolutions, and one of the key achievements of Turing was to invent the Turing machine and define the computability theorem that allowed Turing in the 50s to understand that given the fact that with the Turing machine, so this digital computer, we can compute any computation, any theorem proving. We can represent not only in natural numbers, but with a certain degree of approximation, also real numbers, more complex numbers. So we can play with a certain degree of complex numbers and so forth. And we can represent also letters as numbers. So if we have a machine that is able to translate all those things into numbers and then in 0, 1, so that's very convenient because you can simulate with a switch on off, then what you need, you know that you can compute a lot of problems. And what you need is just having a faster computing and more memory. And this was just a matter of time. So that's why he was able to define the problem in the 50s, even if the computer at the time were not so powerful, because it was just a matter to make them more fast and with more memory. Yeah. And we knew already that from a foundational perspective what we can compute with them. Analog computing was a thing before digital computing. We used the analog computers to do differential equation solving, like if you have to shot a projectile from a ship to another ship or from ground to an airplane, you have to hit and compute very fast, in a very fast way, those differential equations. And so we built them. But once the digital computer were good enough, fast enough to also compute with a certain degree of approximation, the same computation that was done with analog computing, we replaced them. So nowadays there is a return of analog computing, and we may see interesting development there. But when we talk about artificial intelligence, we are talking about something that runs on a digital computer at the moment. There are other paradigms that are emerging. Quantum computing is just a different way of doing digital computing. It's not a real, it's again a leap forward in computational power, not in the, one of the key aspects, for example, in artificial intelligence nowadays, which is power consumption, is rooted on the fact that you are doing a lot of translations to make things computable. And it's very complicated with a digital computer to deal with randomness. It's far easier to do it with natural phenomenon. That's why, for example, and randomness is key in training of the kind of machine learning we have nowadays. So, for example, now there are experiments in the direction of what is called thermodynamic computing, which is a new paradigm based on thermodynamics and using thermodynamics properties to inject randomness at the beginning of the training, for example. This could improve dramatically efficiency. So, if we want to talk about artificial intelligence, we have to put constraints into the conversation. Otherwise, we are talking about science fiction, and we have plenty of science fiction since the beginning. Okay, so I think that the constraints that Turing set in the 50s are still effective. So we're talking about digital computers. We know what we can compute with digital computers, and we are asking ourselves if we can think and speak up to the degree to pass the imitation game. So, imitation game, in the Turing intent at least, is not about proving that the machine is able to understand. It's able to answer questions. This has an interesting impact, but please stop me because
because I would like to circle back into that, because one of the things that I was seeing about the Turing machine that he created, it was about this sort of dialogue and the way it answered to the person somehow. But also what we are seeing right now is somehow this aim to make the machine more human, so natural language processing, to have this blurry zone where the user sometimes is, it feels like it's interacting with something that is a little bit more humanized. It's still a machine, but natural language processing, I don't know if that machine of Turing that had very long time ago created that sort of, kind of sensation, or it was the way that it answered. But right now we're making all these efforts, to somehow humanize technology. What kind of differences from that time until now you see in this evolution? And do you have an answer why we tend to somehow humanize in this kind of way an artificial intelligence?
Okay, this is a very interesting question. And again, I think that the experiment that Turing set and the constraints that he put in the experiment are actually somehow setting the path ahead. So, as we said, we were talking about written language written with a typewriter, so without any hint. And this kind of language has specific peculiarities, if you want. And we need a bit of the tour here. So we think about when we talk about language, we are mixing again a lot of terms. Thinking, speaking, understanding, and so forth. And also language is mainly, when we discuss, written or verbal language. Because why? Because with verbal and written language, we were able to develop things like mathematics, logic, rational thinking, science to a certain extent. So the way we look at language and the way we look at intelligence through the lenses of language defines also the way that we think about the relationship between brain, mind, consciousness, and understanding. I'll make it simpler. So there are two ways of approaching this problem. One is top-down and the other is bottom-up. Mm-hmm. Top-down is if you think that there is that the mind somehow is just an emanation of a perfect mind that knows it all, mm-hmm. and is able to see everything and so forth. Doesn't matter if it's God or not, but if you have the mind, the perfect mind, and then you have different instantiation of this mind through the natural landscape. So you have, if you want to be religious, God, the angels, and then the humans. For example, if you are rooted into the Western religious belief. And then you have different degrees of animals with different kind of capabilities in mind. And then over time, we decided that only up to the man there was a mind, then there was not. Yeah. Up to the smaller form of livings like protozoics and so forth. So if you have this type of approach, you are approaching intelligence like we approach intelligence in the early 20th century. So from a logical and mathematical point of view. So what is thinking? Thinking is mathematical thinking, logical thinking, rational thinking.
Being able to talk.
And language, what is the perfect language? Is not necessarily the language we speak every day, is the formal language, logical language. Okay. The language we speak normally as problems, as paradoxes, and also has inflections, as other things that are happening. But if you are a logician, you want to narrow them down. That's why you go to the written language and you ask questions and answers, and you prove the rationality of the other side and the irrationality of the other side. So if you have this top-down approach to the idea of mind, you develop an idea of intelligence that is beforehand rational.
Yeah.
And this is rooted on religious beliefs, on ideologies, on also some kind of scientific patterns or beliefs. If you think about the way Darwin and Lamarck developed the evolutionary theory in different ways. So Darwin at the end, yes, it's true that is based on randomness, okay? But the idea is that the more strongest survives, means that if you are at the apex of evolution, you are the strongest. And at the end, who is the apex? Is the human, okay? Yeah. It's just another way around to demonstrate that you are on top, okay? And this is one approach. If you have instead another kind of approach, which is bottom up, and you start thinking, okay, but if life started with protozoics, very simple forms, why it evolved? And what are the basic mechanisms of this evolution? So you don't start from above, from the mind, and you go back to the human, but you start from the protozoic and then you go up to the human. Yeah. And then you ask yourself, why you not only have humans? Because it's so evident that we are superior. Why not everybody is a human? Everything is a human. Okay. So the key point here is that based on this approach, you develop a different idea of mind. Okay. Sorry for the long term.
No, it's okay. It's okay.
Now, another author that is very interesting is called Gregory Bateson. Gregory Bateson is many things. Has done researches in very different areas, from biology, psychology, and psychiatrics. He invented the double-bind principle to cure schizophrenic diseases. He started the Palo Alto School, was a mathematician, was a logician, so was many things. And one of the key ideas of Bateson in one of his books, which is Steps Towards an Ecology of Mind, was, okay, let's start from the bottom-up approach. What are the many things that we share with the other natural beings? Yeah. We may discover that what we consider intelligence is not so human, but is very diffuse, shared. And the main idea there was that one thing that we share with everything else is the fact that we are processing information. And if we define a mind based on the capability of processing information, we have a different way of defining mind, intelligence, and language, and so forth. I give an example. If I kick a rock somewhere, the rock moves and goes and have a certain trajectory that is very physical, is casual, in the sense that based on the force with which I kick the rock will go away from me, more or less. But if I kick you or a dog, I'm an awful person if I kick a dog, but if I kick a dog, the answer of the dog is not based on the energy only that I impress. It's based on a reaction. And so Bateson tries to analyze the things that may define a mind. For example, one of the key aspects is that he has an external energy. So the dog reacts based on not only on the kick, but on its own energy and the processing of information. It may go away, it may attack you, and this is not physical. It's not based on physical law. It's based on how you process information. And one of the key things of processing information is that, and this also connects to the information theory of Shannon, is that you have to distinguish what you call information from noise. So, yes, if it hurts, you can feel it, okay? But why you feel it? How you can distinguish noise from information? You distinguish noise from information based on patterns or a difference. And not only a difference, this is a threshold, okay, but on patterns of differences. What Bateson called this a structure. Simple example, if you are in a forest and you see a sequoia, which is a very tall tree, you may not see the top of the tree. You can just see the body of the tree. But based on the body, since you're able to capture a structure, you can argue that there are roots and there is a top. So this is a basic pattern. Another pattern is that you are able to get from a part the whole. And keep in mind this point, because this is actually what LLM does. So you can guess a whole from a part, and this is a very deep capability of every kind of mind. For example, when we talk about language, we talk about spoken language, but actually there is the iconic language and there is the cinematic language. Iconic language is, I'm a snake and my color is red. And I tell you, stay away from me. And I can be a real venomous snake, like the Corallo snake, or I can be a fake venom snake. I give you the same message. You see red, and over evolution, the other have developed a capability to say, if it's red, stay away. Or if I have a certain shape, stay away.
Yeah.
If I show my teeth, usually this is a message that says, I'm going to attack you. Okay? This is iconic message. If you think about cats when they are in love, male cats, the terrible noise they make during night, but the kind of simulated fight they have from each other. So they're moving around. They don't actually arrive to a real fight most of the time, but they do a sort of game.
Sort of dance.
A sort of dance. So this is the cinematic language.
Okay.
Now, if you take the top-down approach, you may think that language comes first. Rational language comes first. Actually, it doesn't come first. It comes later. Okay? Oh, yeah. So from a bottom up. And then the second question is, but why if natural language is so powerful, we still are adopting iconic language and cinematic language? So we have nonverbal communications. And one of the key aspects of Bateson says that probably the reason is that, so the problem with the iconic and cinematic language is that it's not able to negate. Okay, it doesn't allow you to do a negation. So you say, look what I am, iconic.
It's representative.
Okay.
It has a form.
Exactly. It tells you something that is the truth, okay, about what something is or what is going to happen.
Yeah.
Be aware, I'm going to attack you. Don't do it, anything, go away, stay away. The power of natural language is that allows us to do negations. So it's more powerful.
Yeah.
But we still are using iconic and cinematic. Why? And the hint from Bateson is that probably because we use those kind of languages to set an expectation on truthfulness. So let's connect the dot back together. If we're reducing the communication down to written language through a curtain, we are moving away from whatever iconic or cinematic language, so we are not able to set the truthness of the relation. Okay? Which means that, for example, it's very difficult for some people, myself, for example, to be a good liar. I'm not able to lie.
Because you have other representations.
They spot me immediately, so it's a painful existence, not being able to lie. But that's the point. So when I talk to you, you know that I'm saying something that's, you can trust me somehow.
Yeah.
I can try to lie, but you can trust me. And you get this impression not because I say something, but the way I'm interacting with you. So in the imitation game, you're taking away this, which means that the interviewer must make assumptions.
Yes, but I have something that I'm very curious also to discuss on this. Right now, okay, we have the imitation game and we have the LLMs today. Okay. The other day we were discussing about this case, about the fortune teller that DeepSeek is doing in China. I was telling you also that teaching, okay, for me, I was interacting with different students, and one of them said, like, I didn't find answers with my psychologist, and I decided to go to the machine to have the answer, and actually I had it in a more fast way. And said, like, wow, but do you know the kind of journey that you need to undertake with a psychologist? Yes, but I needed to have a solution right away. The part of the case, if you want to tell it, for me, it's better, but this sort of trust, and you mentioned trust before. Of course, you're talking about the different type of languages, but somehow I think natural language processing is having an impact on us, that it's creating this level. I don't know if it call it trust, because for me it gives me goosebumps to say that I'm trusting fully the machine.
You're making assumption on trustfulness. So this is the key aspect. So, and this was absolutely interesting with the ELIZA example that I was talking to you about. So let's go back. If the interviewer in the imitation game wants to spot who is the liar, he makes an assumption that someone is lying. Okay. Or makes an assumption, it may make an assumption that someone is a machine. So it sets the communication based on an assumption.
Yeah.
In the imitation game, I think the fair assumption is that someone is lying. So you can't trust them. In this way, you are having a conversation that tries to make the liar make a mistake.
Yeah.
Okay. And this is the way that researchers are actually testing an LLM.
Yeah.
They're trying to make it answer in a wrong way, or try to force it going the wrong direction. For example, the interesting thing about DeepSeek is that since on top of DeepSeek there is a sort of censorship, you can't ask about Chinese facts like Tiananmen facts. Okay, but Tiananmen is also the name of a starship that appeared in Star Trek series. So you can try to fool the censorship asking about Star Trek Tiananmen. And what happens is that at some point the hallucination goes so far that it actually gives you back information about the Tiananmen facts. So this idea that you're trying to falsificate, to prove that you're going to spot the liar, is still the way we are testing things.
Yeah.
Instead, the basic expectation that we set in the communication, or the implicit expectation that we set, is another important thing. So as we said, the narrower the communication channel, the more the assumption we need to make. Okay. So as humans, our language is always relational. So yes, I can think by myself in a dark room, completely isolated from anything. But if I think between myself for too long, I'm probably going to be psychotic at some point. So language is always relational. So I'm relating to you to do something or to have something. And one of the net results of Bateson studies was that the idea that communication is a message plus expected behavior. The message can be formulated in terms of Shannon information theory. So we know how to transmit a message in order to make sure that no matter the semantic, no matter the understanding, if I say A, you receive A. Mm-hmm. Okay, so we know how to do it.
Yeah.
The expected behavior instead is what, for example, was the problem with schizophrenic behavior. I was so I don't want to go into detail, but the general idea is that there is a wrong relationship, there is a wrong meta-communication inside the family. So I'm telling you something, the message, but I'm conveying you a message, a context that contradicts the message.
Okay.
Okay. So in this way, you are not able to tell what's true, because you hear something from a message, and then you have a contradictory context surrounding it. You're sort of going back and forth between the message and the context, and they are not aligning. It's like saying double. Okay, mm-hmm. This unalignment brings you to a psychotic state. Okay, and so it's important to set the context. And the context, in the case of an interviewer, is someone is lying. But the natural context that we are setting when we are talking with someone is to trust them.
Yeah.
For example, one of the things that happened, so there was a program in the 65, Weizenbaum developed the ELIZA program, which was a very simple program based on pattern matching, was working only in English and German, and was programmed with some basic patterns. And whenever the pattern that didn't match, he had a sort of basic question to ask. So it was modeled, there were scripts that allowed us to model ELIZA in different ways, and one of the ways was to behave like a psychologist, the kind of psychologist that asks you only questions.
Yeah.
Okay, so I give you the example of a communication with an ELIZA. So just a second, I need to, because I think it's, so ELIZA, is something trouble you? And the answer, men are all alike. I'm a woman and say, what is the connection, do you suppose? And they are always bugging about something or other. Can you think of a specific example? So as you see, the pattern here is that I'm showcasing from a language perspective a sort of interest, but I'm not doing anything. Now, one of the effects, which is called the ELIZA effect, was first observed by the author of ELIZA. And it happened that, so I can cite you. So he says, the problem was that the secretary of Weizenbaum wanted to be left alone in the office to talk with ELIZA, because she was very comforted talking with her. Okay. And Weizenbaum wrote that in a book later in the 76. I had not realized that extremely short exposure to a relatively simple computer program could induce powerful delusional thinking in quite normal people. And this was formalized at the ELIZA effect by Hofstadter in the 1995, saying the susceptibility of people to read far more understanding that is warranted into string or symbols, especially words, strung together by computers. Yeah. And the key point, the key difference at that time, so we're talking about from the 70s to the 90s, is that at that time artificial intelligence was based on symbolic AI, so programs. Very simple programs. ELIZA program is just, I think, 100 lines of code. Nowadays, LLMs are based on training, on large corpuses. So they have the capability of creating interaction that is far more complex. But the kind of expectation they are setting into people are the same. So we are naturally towards having a trustful conversation with someone that can speak. And this is the expectation setting, and this is why ChatGPT created such an emotional reaction in society. Because the moment you speak with someone, we talk with someone, so in a written form. First. In a written form is something that you consider, if you have a top-down approach, something that is special to humans. And so if it can speak, it can think, and then we are naturally inclined to say it can reason. But these are different things. Okay, so this ELIZA effect is still strong today. And the example on DeepSeek, so there is this article from the MIT review that was published in March about the fact that they discovered that millions of young Chinese people are actually using a DeepSeek interaction as a fortune teller. It's very interesting. And probably speaking, the answers are not so bad.
They have the data.
They have a certain amount of data.
Yeah.
And this brings me to the other point I want to discuss, which is the famous definition of stochastic parrot. Okay, but I'll stop for a moment here because otherwise I'm talking.
Yeah, no, I think it's quite interesting because we're talking about different levels of intelligence and how we as humans conceive intelligence somehow. At the same time, talking about what kind of experiment has we performed from a long time to try to come out something from the machine that is very even relevant right now, and how language plays into this in the different forms of language, a very important position. But also one of the things that we're saying here is like how actually LLMs work. And I think if I can identify the two main characteristics of LLMs is the quantity of data that they have, okay, and the way that they perform the answers, taking into account that you prompt something, a phrase, and this prompt takes, it is cut in tokens, different kind of tokens, and the result of the answers is a little bit, I don't know if saying probabilistic, is the right way,
or
but it's basically stochastic. There is a way that they interlink different phrases or words that put them together to have an answer. It's very interesting because we were discussing the other day as well, ChatGPT is always going to have an answer, and it's demanded or it's directed to do so, even though it's not the answer that you're expecting, even though that your question doesn't have an answer, it's going to always say something, and say something it's because how it's structured behind. Okay, so
yeah, but the thing is that I mean, maybe the dangerous thing here is that you as a user will think it understands their answer, and where in the reality is just repeating information,
grabbing tokens of different words,
let's say randomly on the data, and not randomly but probabilistic, stochastic, and the answers. Before we get into that, I wanted to go back to the trustfulness that we as humans have on other beings outside, let's say, our community. Because for me, it's always interesting, also has a background on design. It is always interesting how we as humans are able to form a connection with many things, right? Even since the beginning of let's say the Homo sapiens sapiens, it's known that we have this capacity to form deep connections with even objects, but also with other animals, with many things, with We create idols, we create gods, we create, let's say, stories that shape our humanity. And that some says that is what makes us humans, right? The capacity that we have to create stories and shape our world on things that are actually not existing. But it's always interesting to me that we are able to get emotional attached to things that are just things, right? So if you think how important was for a knight their sword, or how important is for so many people just a book, or the things that doesn't have an interaction with you. So for me, we can think that, okay, now we are creating all these new objects that are going to be able to interact with us, imitating our communication. And we are starting thinking, okay, but now the interaction with this type of product is going to change, is going to make all this impact. But for me, it's actually not surprising, because if we are able to get emotionally attached, with I can say that if I don't know, my car, for example, if I have an accident, I just scratch the car, I know I will be depressed like for some days, and it's just a piece of metal. For me, it's not surprising that people are going to be able to form very big, a strong emotional attachment to something that will be able to answer to you, to talk to you. It's not that unnatural, is what I'm trying to say, how we form connections with things.
So I think that it's important. And one of the other lessons from Bateson, was also the father of the ecology revolution and systemic thinking, is, first of all, we need to understand if it's possible to tell a difference between a living thing and an animated thing. Then we can talk about the kind of projection we can have. So let me just drink it.
Yeah.
And the interesting thing is that there are specific attributes that we can use to identify with something that is living. And we don't have time to go into the details, but because we see something that is similar to us. We are symmetrical.
Yeah.
We have a left and a right, and then it's difficult to we can interpret it's a specific language that we can see in another living being. So we can get attached to a living being or correlate to a living being due to this kind of attributes that we share with them. And intelligence is one of them, in the sense that we can spot some intelligence in our dog. He's not able to speak, but he's so intelligent. Okay, we say. This is a way of recognizing the living stuff apart from the not living ones.
Yeah.
Then we can have a sort of projection. As we have a projection towards living beings, we humanize a dog.
Yeah.
We humanize our pets, even if they are behaving in a way that is not human, but we tend to put an humanized thing on top of that. We can have attachment to objects, but not because of the objects, but because of the kind of memories or emotion that brings it back.
Yeah, exactly.
Okay, so it's always based on, and I think you got the interesting thing about narrative in stories. This is another interesting thing that also Bateson tried to define. So we use a story for many things. We need to look back at evolution as well. So one of the key thing of humans as we are now is a feature called neotenia, which means that it takes a lot of time for us to become independent 15 years to become sexually independent, mature, 5 years to being barely able to go around without any serious risks. So we have plenty of time for playing with things. Our brain is just 1/3 of the size of a fully developed adult, so also our brain is very small at the beginning, grows, and we have plenty of time to learn, which has some pros and cons. By the way, this is also something that also Turing noted in the essay, because he was saying, okay, we may think about programming a computer with all the features that can emulate the intelligence, but we can also find another route, which is we may program a digital computer with a smaller brain, like a child brain, and then we can make it learn. The problem was a logician, Turing was saying, if we program something, we can be deterministically sure that it does what we program it to do. But if we open up to learning, when you learn something, you have a certain distribution of possibilities in the learning. So you need to bake in errors. You may do more interesting things, but with a degree of errors, which is true even today. So having the neotenia as a specific feature of humans, and sapiens sapiens is specifically as the longest one, which means that we, evolutionarily speaking, and also in our life, we have a tremendous amount of time to learn and to play with things. A recent theory says that probably spoken language was born out of this game, because you don't have to wait to be able to speak a very complex language to being able to hunt. Otherwise, you're going to die very soon. Okay, we'll not be here. So we were able to communicate probably with cinematic and iconic language from the very beginning in a very structured way. But we had this opportunity to speak, to waste time around while we are children. So this capability of learning is actually something that we are not being able to model yet completely in artificial intelligence. There is a new area, long field of research, which is reinforcement learning, that may have a boost nowadays that can go in direction. So what we have developed so far is instead a very effective way of emulating stochastic behavior. And it's surprisingly going well. So again, let's go back to the history. So what Shannon theory about information was saying, that if we take English, if you have a letter A, you have a certain degree of possibility that the next letter will be a space or a certain amount of letters among the entire set. So it's not completely random. You are reducing the stochastic probability. Okay. And we developed on top of this an interesting pattern, which is, if you want to make sure that if I want to say A plus B, you get the B, it's better if I repeat again a couple of times B. Okay. So to make sure that if you receive a C and a B, you can tell. Maybe 2 times is not enough, 3 times. Which is actually something that we already were doing. So if you think about the drums in the forest, okay, it was a very effective communication mean, and was based on a key feature of most of the African languages, which is they are tonal. So you can, instead of writing letters, you can just have a low tone and a low pitch and a high pitch, which is very useful from a drum perspective. Okay, but the problem is that if you just map the tonal movements, you have the same word that has the same tonal pattern that have completely different meanings. So you have to add other words to make it to disambiguate it. Okay, so repetition, redundancy was a key aspect of the information theory, but is also a key aspect of our language. And this is connected back to LLM. The more you can provide context redundancy, the same word can have different meanings. based on the context. So one of the key achievements of LLMs in respect of the probabilistic approach that we had before, just to be clear, Google Translate initially started with a probabilistic engine based on stats. Okay. It worked quite well. The first release of Google Translate was amazingly capable of, because they were able to compute those statistics on a large corpus of elements. But when we had the transformers technology, so the way the LLMs are built, it proved to be way, way more effective. But it's still probabilistic. Now, there is an interesting paper written by Bender, which is, she's a computational linguist, that was defining the term stochastic parrots about LLM. And I think it's interesting to note a couple of things here. Just give me a second. So the first one is that if you look at the white paper, which is called, let me just recap it, On Dangers of Stochastic Parrots, Can Language Model Be Too Big? You will notice that one of the authors is called Shmargaret Shmitchell. Actually, the problem is she was actually Margaret Mitchell. She worked for Google, and Google asked her to remove her name from the paper. Okay. She refused. She was, at the end, was fired by Google. And so for protesting this silencing of the voice, she changed her name in Shmargaret, is a way in English to say be silent. Now, what's the problem with this white paper and the angry response from Altman? Sam Altman responded to the white paper, I am a stochastic parrot, and so are you, which is true to a certain extent. So the key point is that what kind of expectation do we have in terms of LLMs? Are we expecting a stereotype communication? Are we expecting, which is called, we call it natural language processing, or are we expecting an understanding, an intent, or having our own intent in the communication? The answer is not. They are stochastic.
But they are stochastic, but the perception is a little bit blurry between one and another one.
But there are 2 points here. The first one, of course, is based on intention. I talk with ChatGPT thinking that of DeepSeek, thinking it as a fortune teller. I'm setting a set of expectations, of trustfulness, of outcomes, of certainty of outcomes, and so forth. So this is based on myself. But the other point is that stochastic communication is actually not something that we are avoiding in our normal communication. So it's a feature.
Yeah. It's a feature.
When I was a child, I was in a Catholic school. So among the other things that we were learning, we were also learning to sing Christian rhymes and so forth. And one thing is that melody-wise and wording-wise, once you have learned a good amount of them, you can guess. I was able to sing along whatever new rhyme they were playing, because the melody, where it was going, and the words you could guess to a certain extent. With just a small delay, I was able to go along, and in very small, tiny delay. So this kind of communication based on stochastic response is pretty normal. Yeah. Most of the time we do things in this way.
Yeah, no, I think
and so it's a normal feature. So my point here is that, yes, if you want to be very precise on the meaning of understanding, they are not understanding. Yes. It's useful having a stochastic conversation, could be. It's useful as much as a communication where you have a clear intent, a clear setup of trust, a clear understanding among the parties. No, it's not like that. It's a different thing.
Exactly, and you are aware, we might be a little bit aware of that. My concern is the rest of the population.
It's not.
It's not. And there
it's
is
like
a
the
lot
secretary of Weizenbaum thinking that he's talking with the psychologist, because he's behaving like, to a certain extent.
But the thing
it's
is
good
also,
enough.
Do they need to? I mean, for so many cases, you don't, really need to understand, or you don't need really care that you are talking with a thing that is understanding you. If at the end of the day you are receiving the input that you need to.
Depending, I think
It
I
depends on the cases, yeah.
I completely agree, but it depending on the context. If you're talking about having a normal interaction to be the chat GPT of the situation, like a sort of POW to co-create something, so you are giving creating this feedback loop of thinking with the machine somehow, it's okay. Where you are delegating or giving responsibility to the machine in other forms, it's when it gets dangerous.
Yeah.
It was the bias arise is when polarization may arise, because even though those machine has a bunch of information, okay, we don't know actually where are the weights of the information depending on the context.
And actually,
so
they are trained
agree.
depending on the data that they are trained and the things that we are getting into. That you can say that some of these models are going to be trained to behave on a specific way, to give you the answers that
right now they are very generalistic, and this is the
not so
much.
generalistic
I mean,
no more.
generalistic
So they are,
in terms of what you can do.
I mean, what we see, at least in this part of the world, that worries about DeepSeek is that we know that they have this sensor, right? And
Yeah.
so there are going to be a lot of information that people that are going to interact with this model, in theory, are not going to be able to get. And if you base all your life on talking with these things, you are just going to get one part of the reality. But of course, we see this also with social media now, so it's not nothing new.
Yeah. I think the conversation can get really emotional, and let's make some examples. So to make it more effective. So first of all, are there any scenarios in which this kind of stochastic behavior can work safely? So I give an example. If I go to a party, I'm invited to a party by a friend of mine, and I don't know anybody else except my friend. And I'm going around and listening what they're talking about. Maybe are talking about things I'm not so familiar with. But if I'm not a shy person, I will try to listen. At some point, I will try to say something. What's the consequence if I say something wrong? I need to be careful, because if I say something wrong in a context where I want to enter, if I say something stupid, people will push me back. But if it's an informal party where you can talk about anything, what's the consequence? So another point is that, again, looking back at the imitation game, what's the setting of the imitation game? There is no consequence in the game, because the only point is that to win the game, which is spotting the liar. But there is no real life consequence, or there is no imprisonment of the male acting as a woman, or the computer, or killing, switching off the computer. So there is no consequence. So again, if we set up the conversation, the stochastic conversation, in a setting where there is no consequence, we can do useful things. We can avoid boring work. The problem gets a bit different once the outcome of this interaction may have some impact on your life. So talking with a fake fortune teller, I mean, it's like talking with the fortune tellers to a certain extent. So depending on how much trust you put in this kind of relationship, you can have very bad consequences, or it's just an entertainment form.
Exactly.
So one of the things that the LLM has been proved very capable of is misinformation. They're very talented. And by the way, the funny story is that if you remember about the story of OpenAI, before Altman forced the release of ChatGPT, they already got ChatGPT working, and they were already proving that it was capable of producing financial summaries about stock market, or making summarization of other facts in a so effective way it was very difficult to tell if it was a human or not. And also telling if it was completely the truth or not. Okay. And they said, we have achieved these results. We are not publishing the model and the training to everybody openly. You can ask. So they were quite conscious about the real power of this thing. It can summarize, it can write things in such a way that it seems to be made by a human. It may seem also the truth, but it's not necessarily the truth. So the key feature is misinformation.
Yeah.
Okay. So that's the basic feature. So if you are aware of this feature, you can use it very effectively. Because if you want to just produce gossip, what's the consequence of gossip? No, nothing. Or if the kind of content you're producing is just to fill the void, what's the problem? It's very effective.
Yeah.
But if you're using a tool that is very good at producing baked content or faked content to do more serious stuff, you're introducing a risk that you need to mitigate. And that's the paradox we are always in when you're using, LLMs for coding or LLMs for doing scientific research or things like that. Yes, it may write a lot of things. It may do a lot of things. Some of those things may be right. It may avoid you a lot of boring work. Mm-hmm. But there is also always a threshold. Sometimes the threshold to correct the output is so high that you would have been better at doing it by yourself. Sometimes it's convenient. It's good enough to have it. But you are talking about an interaction with a tool where you are an expert in some field. You know that is a tool that is built for doing things that are not accurate, and you're leveraging what is good in the tool. Yeah. So you're setting the right kind of interaction. If instead you're thinking you're finally found the God, remember, top-down approach. So you are thinking now, if it speaks, it thinks, and it knows it all. God. We made it. Which is the marketing push towards behind those kind of tools. Again, it's always important to link those things to the ideology behind. Yeah. So, and that's why it's important also to have this vision.
It's also regarding the access those tools right now have in the society. But before entering into something else, I would like to make a question regarding, do you think there is a sort of merit, concern regarding all the reliability we're given to the use of these tools somehow, that it's going to decrease somehow our cognitive intelligence? And there is a concept that emerged in one dialogue I was having about stupidity. Okay, has delegating too much to this machine and to those machines, and how actually we are using or not our creative thinking and our brain in all the processing. What is going to happen tomorrow if we just rely the most of the intelligence to a machine and not to us or the collaboration between the two entities?
So, again, we need to think about in the context of LLMs and in context of large AI. In context of LLMs, since they are tools built for doing summarization at the end, or having a good enough stochastic prevision of what's next, the next token is called. They are useful, but they are terrible if they're used to play or learn. So again, we take a lot of time playing around as humans. When we are a child, up to when we have to develop specific skills, we need a lot of training, a lot of exercise. Yeah. Removing the exercise is not making us better, because we need exercise. Yeah. We don't need to give answers. The point is not the outcome, it's the playing. Yeah. It's not winning the game or losing the game, but it's doing the game. Yeah. It's the exercise. So the usage of LLMs into educational space is challenging because, yes, you can focus on other things, but it's important that you focus on learning in any case. So if it's used to fake the outcome because you're measuring children by outcome, that's problematic because you are not paying attention to the key aspect, which is learning, exercising yourself. Yeah. So it's always a balance. Which kind of capability you want to grow? We hear people saying, "Bah, it's like using the calculator." Okay, where before the calculator was available to everybody, we have to learn how to do things. Fine, but learning how to compute is something that requires a lot of exercise if you want to do it correctly. Okay, we decided it was not worth to put all this effort in computing because we can have a reliable tool. We need to have basic understanding of how to compute numbers, because even using a calculator means that we need to have a basic understanding, but we can delegate to that. Language is a different beast. Natural language is a different beast. So being able to, the language is a very useful tool to exercise the thinking, for sure. So it's one of the very effective ways to exercise the thinking. Written language is a even more interesting tool to exercise the thinking. It's a limited tool because you have to think in a linear way, in a sequential way, so we may debate. But it's a tool to exercise your thinking. How can you exercise your thinking if you're delegating the writing to someone else? Exactly. I'm open to an answer, so I'm not saying that, oh my God, terrible times ahead, we are not. But we need to think about the problem and how to approach the problem. So having LLMs writing the essays at school, yes, it may work, yes. If you spend the extra time doing something meaningful, then we may question, what was the goal of writing an essay? Was a tool the essay for doing what? So I'm open to this. Another thing is the general artificial intelligence. So the other things that are emerging. I didn't answer completely to your question, but there is another aspect which is important, which is the ecosystem thinking. And if we concentrate on the intelligence, which normally translates into language, understanding, and so forth, we are thinking about a very small portion of intelligence and the ecosystem around it. I like the idea that we can talk about brain, mind, and consciousness. And again, I find very interesting the definition of consciousness coming from Bateson, which I can translate in a more modern way, like hyperfocus. So one aspect of what we define intelligence is that our capability to define a goal and build the path towards the goal outcome, and also build tools to achieve the goal. Okay. Which is something that is also available in nature, but it's a sort of overgrown capability in humans. And if you think about technologies as a way to reach a goal, and the fact that we are building very effective technologies to reach a series of goals, this is an important feature. But what's the problem with this feature? Is that it's hyper-focused. I give you an example about the thing, the concept of total mind that was coming from Bateson. So think about two activities. One is listening to music. When you're listening to music, and when we're having this conversation also, you're able to cut aside all the other noise around. You can focus on a specific set of things that are happening and are coming through your senses. I don't care about this underlying noise that I can hear if I concentrate on that. I can just focus on if you think about the music. I don't know if you've ever done the exercise to listen to specific instruments in a song, okay, with just your ears. Okay. You're able to focus very narrowly to a specific subset of things that are coming through your senses. Yeah. When you do a meditation and you try to reach a mindfulness status, a sort of status where your thinking doesn't overwhelm you, okay, you're actually lowering your consciousness. You're feeling connected to everything around you. Okay? So your hyper-focused status just slow down, and you are connected to the environment, to the things around you, in a more deep and profound way. In an unconscious way, in the sense that you don't have verbal thinking going around. You try to suppress your verbal thinking. And this hints you to the direction of what Bateson called the total mind, which is a mind that also goes around, above, and to a different kind of level in respect of the individual being. And this is the ecosystem. And the interesting thing is that the ecosystem has a sort of mind by itself. The example is, if evolution is set only by the outcome of the most successful being in doing something, at some point, like humans, we are so successful that we have removed almost anything else. But now you have a sort of feedback mechanism that resets the equilibrium in an ecosystem, because you don't want a species, any species, to overcome all the others. So there is a sort of equilibrium, retrofeedback mechanism. And this is a sort of kind of mind because it has an external energy, it has a capability of processing information, not just. So the auto limitation that species get in an ecosystem is of a different kind of mind. So the problematic point we are in now with artificial intelligence is that artificial intelligence is not connected to the ecosystem. It's not aware of the surroundings. And this limits a lot the understanding. So when you talk about something in a written form, let's go back to the imitation game, you're narrowing the expectation. Bender, in the essay about the stochastic parrot, as an improved version of the imitation game with the super intelligent octopus. So imagine this scenario, which is an evolution of what is called the Chinese box, which is another evolution of the imitation game by Searle in the 80s. Imagine this scenario. You have two people, a man and a woman, stranded off two different islands, okay? And they are far away. They can't see each other. They can't speak loudly with each other. But they discover by miracle that someone has left an under the sea cable that allows them to transmit with Morse. Okay. And so they start to communicate with each other through this cable with Morse, so, you know. And let's imagine that under the sea, there is a super intelligent octopus. By the way, octopuses are very, very intelligent.
Yeah, I know.
And have a distributed brain, very interesting. So imagine that this super intelligent octopus is boring, doesn't know what to do around. And so it finds this cable, and with this tentacle, it senses that there is something going on in the cable. And so it starts understanding there is a pattern of communication. It doesn't speak the language of the humans, but it starts understanding the pattern and spend time training on this pattern. At some point, it's so bored that it decides to intervene into the communication. So it cuts the line, and with the tentacle is able to provide fake answers to the question on one side and the question on the other. So, and faking the communication. This goes well if the humans do not relate to things happening there, or to things that require external knowledge. For example, that is going, Bender is giving, is that imagine that on an island, a bear appears. And the woman is asking the man what I should do with the bear. And the man may have a previous knowledge that has not been going through the line before and can provide an effective answer. But the poor stochastic super intelligent octopus doesn't have this context. He may answer something that they have maybe talking about in other contexts, like you can hold a stick and try to fight back the bear with a stick. But it's not such effective. So the general point is that, okay, if we want to ask too much to imitation game, so to be able to understand the context, to get a context, to have a previous knowledge, okay, we are reaching the limit. Now, the problem with LLM is that they seem to have a wider knowledge, because they are trained on a corpus of things that is quite large.
Yeah.
But the question is, how much did we digitalize our knowledge? And which kind of knowledge they are accessing? Because that's the tricky part. And one of the key features of the narrative is that our consciousness allows us also to reduce the number of things we want to talk about.
Yeah.
So when we describe something, yes, we are taking in consideration all the possible inputs that we have from the sensorial point of view and whatever, but we narrow it down to a specific set of attributes. And the description can be as descriptive as the phenomenon itself.
Yeah.
Okay, it's a reduction. So, and this is one of the key aspects of the mind. So being able to get input from the senses, intercept the differences, build a structure, and on top of the structure, do a reduction into a description that is good enough to describe the phenomenon without being the exact phenomenon. Okay? You have less information.
Yeah.
Okay. And this is one thing. So being able to describe something as is connected to a stochastic capability, because at the end you're trying to get the part for the whole, you're getting a reduced stochastic distribution, so it's something that it seems to be very capable of. One of the key features of transformers is that it revealed us how the pattern recognition of languages works. Okay, the fact that we can translate from a text to an image is something that we intuitively already knew, because we have been speaking a lot about the language of music, the visual language of a picture. Okay, so we understood that there was a structure there. And Transformer gave us back a practical way to identify those structures and translate among them. Nice. Is this understanding? Not yet. No. So again, we need to use those tools for what they are capable of. And we need to think about, what do we need? So having a translator between different languages, natural languages, text to image, text to video, text to music, music to video. Who cares? Okay, it's amazing, the transformer technology. So it's a great achievement. I don't want to underestimate it. So it's incredible. And it also shines a light on one aspect of our key capabilities. Run in an emulation mode, because remember, it's running on top of a digital computer. Yep. There may be development of neuromorphic CPUs that mimics the brain. I don't know. We don't have them now. So the context is important. So narrative is even more than a description. Is an explanation. An explanation is a lot of descriptions combined together. It's an interesting way to encode information and pass this knowledge towards generations. So the next thing to me is that an intelligent computer should move towards being able to narrate things. Okay. But we need computers that are more capable also of getting an understanding, playing around, having more wider context, which is not based on books.
Yeah.
Okay.
I know.
You remember the old saying, say, if you study a lot, you read a lot of books, but you don't have any practical experience.
Yeah.
You know, my grandfather was used to say, you have studied a lot, but you don't know real life.
Yeah.
Okay.
If you're not outside the world, the real world.
You are not able to interact, to survive, if you want, or to be able to get there. And we are in the same situation now with LLMs. They are good enough. They read a lot of books, but they don't have any experience in real life. That's why I think reinforcement learning is now interesting, because we have a way probably to use GPUs to do reinforcement learning. That was one of the key problems. We may see interesting development there. Not to say that we should throw away LLM. LLM will remain a key capability we can build on top.
Yes, I think
for what they are able to.
Yeah, there are, yes. I think they will remain, and it's the starting of something in terms of. I'm going to talk about in a more human side kind of way of behavior and expectation. Somehow the relying or the relationship or the interaction we're having with the machine is driving us as humans into something that we don't know what is the evolution, but we are asking ourselves our questions on the impact. Probably, I don't know, in the epoch of the calculator, we ask ourselves the same kind of questions. But right now, this space of artificial intelligence is inviting many other dimensions that probably the calculator didn't do.
Absolutely.
Okay, so this is one of the things that I foresee, like trying to understand, okay, how reliability, what is this concept of stupidity, what is the concept that big tech is bringing in terms of agentic AI, agents, and the part that you can delegate all the decision making, taking into account that I'm very aware that agentic AI is not going to be successful until you have the data working the proper way, okay, and the connections
Not only,
in a proper kind of way, and actually the scope of that agentic that you want to do. So we have right now many things on the plate, let's say, and it's very interesting to see not only from a technological perspective, okay, but also from a human perspective, who has access to those technologies, what are they perceiving, how they are executing, how much responsibility or reliability they're giving to the machine, because that is actually what is going to draw the future scenario of what is going to come. Because it's not a case, I think, that the research company that OpenAI intended to build, or the other research companies that are rising that in the beginning were not non-profit and now they're becoming profit, they are deciding to test all these things, okay, those tools, let's say, that before in the innovation path of 10 years ago we used to test with early adopters. They are testing those models with the risk and the potentiality within the society. So I think it's what is going to happen in terms of, again, behavior and expectations of humans is going to draw, and it's actually drawing how those technologies are going to be shaped, besides all the technical part and so on. So my curiosity is from the technological perspective, from the intelligence perspective, but from the human and society perspective, what is the kind of connection that we can make?
Just before that, just want to add in top of that question, because I think, and we are going to see this in the next year, or next 2 years, maybe I don't want to say dramatic change, but probably an important change on what is going to happen with these models. Because one of the evolutions of the LLMs, and we were talking about before, about 2 days ago, Google released their new system to control robotic systems, that we can say is an evolution of the LLMs, but it's a technology that will go and run in parallel. But what I'm trying to say is that we are going to see in the next future that these systems are going to be able to go out in the real world and are going to be able to start learning in the real world about new things. So it's like we are going to start having systems that are going to be able to learn, to get a lot of new data, visual data, that is not going to be only
in the city, for example,
talking
China
about
and New
robots
York
in the
is
cities,
one of
but
the
we are not only of the wave of humanoid robots that everyone is talking about these days is going to happen, but many systems that are going to have this system where are capable to understand much better their context and learn from their context. So if we add to that, to all the knowledge that we have, and we have been training these LLMs that we say are the books, okay? Now we are adding also a new layer of new knowledge of the real world and in real interactions of humans Because if we imagine we are going to have these systems also here, watching us talking and interacting in the real world again, understanding gravity, understanding the complexity of the reality, and learning about this, then we can expect that we are going to have systems much more smarter, because they are going to be able to understand the context much better. So are not going to be just a box closed with data, limited data that arrives from internet, but also
cameras, sensors, and whatever situation.
trained on real-time data. And
Perfect.
that could open many things.
Okay, so let's also talk about the forces at play here. So there are economical forces, there are physical constraints or technological forces and technological constraints, and there are expectations on people. Okay, let's start from the technological constraints. So we said that let's limit it to digital computers. So we may have a future paradigm, we don't know. Okay, in the current context, when we talk about in context of digital computing, if we look at the definition of artificial intelligence, we have three main branches. So one is symbolic AI. Symbolic AI was the winning ideology of the first wave of artificial intelligence from the 50s to the late 90s. And the key feature of symbolic AI was that it required a lot of human work beforehand and required a lot of computing power whenever you want to ask something or having a result. The pro was that it give you only the right answers, if it can, or it says I can't. Okay, I'm oversimplifying, but the idea is that, and the outcome of the symbolic AI phase was what we call now algorithms in general. So if you are able to use Google Maps, it's because of symbolic AI. If you're able, to a certain extent nowadays, but it's more complex, but if you're able to use an application to do some business processes because of symbolic AI. It takes a lot to program them, but you have an expected behavior that is deterministic. And you need a lot of computing power to do very complex thinking. Okay, and this was the limitation. So there were a class of problems that were impossible to be solved there. Pattern recognition proved to be impossible to be resolved in a good enough amount of time, either because it required a lot of effort from humans and a lot of computing power for computers to solve it. Robots in the 80s or in the 60s and 70s were able to recognize shapes. We had them, but we're not able to use at large. So there were constraints. But as Turing said, this is one way around. The other way around is to have the machine learn something. You spend less time in programming it, and you have to wait, and you spend a good amount of time training it. And we have two main branches here. We had genetic programming, which was mocked after, let's say, DNA evolution. So you write the first program, the program mutates, and you select over generations the ones that are more nearby your expected outcome. It takes a lot of time, a lot of computing power, and it's like throwing dice at some point. So it's very complex to predict how fast it will take to get the right result. So it was an interesting field. It's still around because there are a class of problems that may be solved very easily in this way. But usually we don't talk about genetic programming nowadays. Then there was machine learning. Machine learning, now we are using machine learning to talk about different things. Originally, it was based on probability. Okay, we had also a deterministic way to approach probability. So we have probabilistic logic, we have fuzzy logic. So we have an approach that was towards learning, but based on symbolic AI. And the first iteration, statistics and so forth. Then we had the deep learning approach, so using neural networks. Neural networks were not new. The first famous neural network was the perceptron in the 50s. He lost the game of getting investments and funds. So at that time, the side that won was symbolic AI. The problem with neural networks that we knew from the second half of the past century was that it's easy to model a network. It's hard to train, to decide how to train. So the perceptron was great because it was a single layer neural network. And the inventor had a specific way of training it, an approach, an algorithm for training it. The problem is that having a single layer proved to be capable of some kind of pattern recognition, but not the OR, for example. And the training was not suited, the way it trained it was not suited to be applied to multi-layered. We had to wait almost 20 years, 30 years, to have reinforcement learning. So a practical way of training multi-layer neural networks. And once we got it, Hinton was the inventor, among the others of this one, was not enough again, because we had to wait until we had a vast amount of data to apply on top of this kind of learning. So it took Google, let's say, to buy actually the company founded by Hinton and other two students to ignite the revolution of machine learning with neural networks based on this kind of learning strategies and drive them to transformers and so forth. So we're talking about a specific context now. The problem with this approach that became a sort of an ideology, because we need to remember that Altman, for example, is one of the advocates of effective accelerationism, and is saying that this kind of machine learning is the definitive way of doing stuff. There is no need for anything else. We just need more computing power and more data. And we can do everything. So one of the nice things of this kind of neural networks is that they allow you to define a function based on the input variables and the expected outcome. Then you may have different strategies, but what they are building is the inner working of the function to a certain degree that is good enough. So they're very effective when we don't know how to model the function. If we have a way from a statistical point of view to model the function, it's pointless to train and spend money or running this. So those kind of neural networks are very good in the sense that they take a lot of time from a human point of view to prepare them. And there is a lot of hidden human labor on classification and so forth. They require an incredible amount of energy to train them, but they have they can have good enough energy requirements and computing requirements to operate them. So there is a disproportion between the training effort and the execution effort. DeepSeek proved that not only it was able to reduce the training effort, but dramatically also improve the efficiency of the execution of it. So these kind of constraints put very basic questions about who is going to actually being able to use them. If those kind of pros and cons do not change over time. So we can have a dramatic improvement. I don't know. DeepSeek was somehow out of the blue. Then we made debate about it. But so are we going to have further improvements in the cost of running them or training them? If yes, we can think about a more general availability. Now there is reinforcement. Backpropagation was the training algorithm. Now we have reinforcement learning, which is something that we thought about a long time ago, but there was a computing issue because we need to run these kind of models in a sort of simulated world.
Yeah.
Okay. And creating those simulated worlds and running exercise on them before putting robots outside was very costly. because we have to run the simulated world on CPUs
Yeah.
and the training on GPUs. Now there seems to be an opportunity to run also the environments into the GPUs themselves. By the way, GPUs were the third factor of this revolution of neural network, because neural networks are large computational matrices with not integers, so with not natural, with real numbers. So you have to run things that are not the best things to run on top of a CPU. The moment we were able to run those things on top of a GPU that was actually meant to run in parallel a lot of floating point operations, we got the boost in CPU capability that was not available before. So now there is a chance that reinforcement learning running the environment and the training on GPUs can have such a boost to improve these kind of scenarios. Now, the third point is that where are going the investments? So the economics of things. We're in a sort of bubble, yes. The numbers that are floating around are somehow inflated.
Yeah.
Okay, so if you think about the number of CPUs that NVIDIA is selling, they are not in any server, and not all put in servers because they are sitting somewhere. Okay, we don't have the kind of infrastructure that matches the number of CPUs that has been sold, and all the investments they are trying to do in building data centers have physical constraints, because you need energy, you need water, you need technology to do those things. So it's easy to talk about the pervasiveness of AI in abstract forms or in a sci-fi mode, but then we have to go to the real end. So nowadays everybody can use ChatGPT, but ChatGPT has no connection with the world, all the things that we said before. So how we can move forward? How we can have something that interacts with the world, learns like we do, or is capable of doing like we do. There is a lot of things we need to do before getting there. But the basic problem is always for doing what? Why? So the driving force nowadays towards LLMs is the illusion that we can replace a lot of humans with LLMs. Less developers,
Let's say with technology, right? Not
less employees. And this is, but the point is, what is the myth behind it? I call it the one company myth.
Mm-hmm.
If you think about one of the driving forces of capitalism was technology, how to replace manual work with industries, with automated processes, and the humans were unavoidable side effect of this kind of thing. So you need to have people running those machines. Okay, but the goal of an owner of an industry was to have less humans and more machines. Okay, and this is a driving factor as well. And this is very Western. So it's the way we intend again, it's hyper focused. So what's the goal of an industry? Is to make money, is to make more throughput of goods. Okay, and this was fine if you had an explosion of population. Okay, but if your goal is to produce more and more goods, it's fine if someone can consume them. Yeah, otherwise, you're producing goods that nobody's going to use and nobody's going to buy. Yeah. Again, if you just look at the narrow, hyper-focused view of someone that builds a corporation to produce goods and has the only goal to produce more of them, is interested in throughput. And whatever limits the throughput should be put aside. If the humans are too slow, you want machines that go faster. And this is sort of myth, because of course there are areas in which machines are very effective nowadays. You can also add robots. You can have more smarter robots. But you need to think in a more ecological sense if you want. The moment you replace all the humans with robots, who is going to buy your things? And why? They need money. They need the labor in the case. So are we able to shift the work accordingly? Otherwise, you have an over-optimization on the short term, but you're not producing any output. So my point is, if we look at the example of the, so this is also rooted in another interesting thing. So the model, the pattern and the myth we are shaping artificial intelligence is mainly based on the idea of master and slave. We want a computer that does things instead of us. And if we go in this direction only, of course, the direction brings us to the point where we need more capable computers, because we don't want to do almost anything. And then the question is, what's left for us? What shall we do once the computer does everything?
To do so, sorry, continue.
No, so the point is that, is the paradigm master and slave the only one? Can artificial intelligence be used to do interesting stuff as humans? Of course, there is an economical driving force that goes in the one myth, in the one company myth, that says, no, the goal is to increase the throughput of things. We need to do more with less humans. We need something that is reliable, so execute our orders, master and slave. But it's very narrow as a perspective. So computers can do more interesting things for us. So to me, the debate on AI replacing humans, or what's going to happen to the kind of labors we are accustomed to, has to be connected to the fact what is meaningful for us. There will be driving force going in this direction. Fine. They're huge.
I strongly believe that, well, we have created machine with that intention, but if we don't find the way of complementarity with these new machines, it's going to be very difficult, and it's going to happen probably what you're saying. And unfortunately, we need to close because we're arriving by the end of this conversation, and very interesting conversation. Thank you, Alessandro, for giving us a lot of inputs on many things. I do have two other final questions, but in a more kind of open kind of way. It's like, what do you, as Alessandro, imagine the future right now with all the things that we're seeing right now? And what actually concerns you right now about all the things that we're living?
So, the reason why I loved computer and I entered this field, and I've been spending my past almost 40 years playing around with those things, is that I like computers in the way that they can create a playful interaction. And they can allow me to think about things or explore things. So if I have to express a wish about the future, I would like to have not boring technologies. Okay, technologies that are not boring. So not to do stupid things or boring stuff, but also to stimulate things and be playful and being able to spark interesting thoughts in my mind as well. So not a slave, but a sort of stimulating partnership, if you want. Okay, that's my wish. What concerns me? Concerns me that nowadays it's very different to have a non-emotional reaction of all those things that are happening, and it's challenging to distinguish noise from reality. And therefore, it's very difficult to tell and to focus on what really matters, and act on that. So what we should be concerned about? To me, first thing first, I'm not so much concerned about LLMs in the sense that, yes, they are tools of mass disinformation. Once you are aware of that, you can play with them. Okay? You can build guardrails around them. If I have to express a concern, is that we can't have system going around in the world based on the kind of rules that we have now. So we need to make those things more safe. If they are interacting with living beings or they're interacting with the real world, or have very deep and concerning side effects. I don't agree with the effective accelerationism idea that we just need to push more faster, because just going faster will solve all the problems. That's my concern. We are playing with tools that may have potentially very dangerous impacts if connected to real systems or the world. Not to say that the misinformation misuse that we have now is not a concern. It's actually a concern, but we can work on it because we know it, we know how it works, we know what it does. But if you think about the future, we need to be very careful in these kind of things.
Right. Thank you very much again, and nothing. I hope that we can continue the conversation from other subjects for sure in the future.
Okay. Thank you very much
Thank
for
you,
hosting
Alessandro.
me.